Today we shall study about electrostatic shielding in electrostatics. We consider conductor with cavity with no charges inside the cavity. A remarkable result is that the electric field inside the cavity is zero, whatever be the size and shape of the cavity and whatever be the charge on the conductor and the external fields in which it might be placed. The result is that the electric field inside a charged spherical cell is zero, but the vanishing of the electric field in the cavity of a conductor is a very general result. A related result is that even if the conductor is charged, all charges are induced on a neutral conductor by an external field. All charges reside only on the outer surface of a conductor with cavity. Whatever be the charge and field configuration outside, any cavity in a conductor remains shielded from outside. Electric influence the field inside the cavity is always zero. This is known as electrostatic shielding as shown in the figure A and B. Now, dielectric and polarization. Dielectric and non-conducting substances in contrast to conductors, they have no charge carriers. When a conductor is placed in an external electric field, the free charge covers move and charge distribution covers move and charge covers and free charge covers move and charge distribution in the conductor adjusts itself in such a way that the electric field due to induced charges opposed the external field within the conductors. This happens until in the static situation the two fields cancel each other and the electrostatic field in the conductor is zero. In a dielectric, this free movement of charges that possible. It turns out that the external fields induces dipole moment by a stretching or reorientation molecules of dielectric. The collective effect of all the molecular dipole moment is net charges on the surface of the dielectric, which produce a field that opposes the external field. It only reduces it. The extent of the effect depends on the nature of dielectric. To understand the effect, we need to look at the charge distribution of a dielectric at the molecular level. The molecules of substance may be polar or non-polar, as shown in the figure. In a non-polar molecule, the centers of positive and negative charges inside the molecule has no permanent or intrinsic dipole moment. Examples of non-polar molecules are oxygen and hydrogen, molecules which because of their symmetry have no dipole moment. On the other hand, a polar molecule is one in which the centers of positive and negative charges are separated even when there is no external field. Such molecules have a permanent dipole moment. A ionic molecule such as HCl or a molecule of water are examples of polar molecules. On an external electric field, the positive and negative charges of a non-polar molecule are displaced in opposite directions in opposite directions, the displacement stops when the current force, when the external force on the constituent charges of the molecule is balanced by the restoring force, comes internal fields in the molecule. The non-polar molecule of the non-polar molecule of the non-polar molecule develops an induced dipole moment. The dielectrics is said to be polarized by the external field. We consider only the situation when the induced dipole moment is in the direction of the field and is proportional to the field strength. Now the substances for which assumption is true are called linear isotropic dielectrics. The induced dipole moment is different molecules add up, giving a net dipole moment of the dielectric in the presence of the external field. A dielectric with polar molecules also develops a net dipole moment in an external field, but for a different of a region. In the absence of any external field, the different permanent dipoles are oriented randomly due to thermal agitation, so the total dipole moment is zero. When an external field is applied, the individual dipole moments that to align with the field when summed over all the molecules. There is then a net dipole moment in the direction of external field. It means the dielectric is polarized. The extent of polarization depends on the relative strength of two mutually opposite factors. The dipole potential energy in the external field tending to align the dipoles with the field, and thermal energy tending to disrupt the alignment. There may be, in addition, the induced dipole moment effects as for non-polar molecule, but generally the alignment effect is more important for polar molecules. Thus, in either cases, whether polar or non-polar, a dielectric develops a net dipole moment in the presence of an external field. The dipole moment per unit volume is called polarization and is denoted by P for linear isotropic dielectrics, P over Xe, where Xe is a constant characteristic of the dielectric and is known as the dielectric susceptibility of the dielectric medium, as shown in the figure. A dielectric develops a net dipole moment in an external electric field.